chapter webinar. We're hosting it here in our offices in Red Engineering in London. You're all very welcome. The audience, for the audience here and for everyone online, we have Stephen Parker, who's going to present data centers and water, a turbulent relationship. Please feel free to put your questions in the comments, but for the in-person, let's try and save them towards the end, and then I'll try and moderate somewhat, but I don't mind it if we chat. I know Stephen doesn't either, so feel free to contribute if you like. And without further ado, Stephen, over to you.
Said.
Oh, actually, one check. Can I just get some thumbs up for hearing us online?
Yeah, that's all good. Yeah.
Thanks, guys.
Okay, so I'm going to start with the bad bit. Everyone knows there's a lot of media out there at the moment, and especially recently, about water use in data centers. A lot of that is focused in the US, but then there are also regional pockets of it, both in the UK recently. Again, there's a lot of data center hatred spread in sort of Ireland and Amsterdam, and I think some of this it's not positive to what data centers are trying to do, bearing in mind that nearly every interaction that we do either online or with each other now all goes through the internet, and therefore through a number of data centers which may or may not be using water. And I think a lot of the confusion comes around whether a data center uses water or consumes water, and that's hopefully a definition that I'll sort of try and clarify in a bit. But yes, there's plenty of media articles. This was one of my favorite, mainly because it has my baby, which is the liquid cooling suite at Global Switch, on as the main picture in a data center that doesn't use water, but we will be. And it has a really nice example of how it thinks data centers work with water, which demonstrates a nice closed loop system, but not quite. So it's a bit confusing, but hopefully we will try and clear that up today. So very simply, water use and water consumption. Again, it's probably a bit of terminology, but and I think there's a lot of confusion, and especially in the articles and even in some of the trade journals I've seen. And I've sort of categorized it as this: water use water is used as the heat transfer medium between cooling and heat rejection units. So whether that's CRAHs, fan walls, chillers, dry coolers, other things like that, but generally closed loop systems. So ones that are using water to move that heat around, but actually consume very little. See, I've started myself off, so we'll see how many I get to towards the end of actually getting it right. So yes, so using water is one thing. In the same way, we will have boilers at home that circulate warm water to heat our houses. Water use is a sort of a fundamental part of most cooling systems. The other definition then is water consumption. So that is water which is evaporated and therefore consumed to provide cooling at the heat rejection plant. So whether that's cooling towers, adiabatic chillers, IECs, or any other thing, heat rejection device. And again, that takes water supply either from a number of sources and uses that to reject heat via evaporation into the air. So,
honorary.
We won't judge. So fundamentally, that is what I am proposing as a sort of definition, and those are the definitions that I'll be trying to stick to throughout this presentation. I probably will get it wrong, so please correct me or ask me questions at the end if that is the case. So the main question I had: are data centers which consume water more efficient? Well, that depends on your definition of efficient. Depends what you want to look at as your prime selection choice when it comes to the data center. Are you looking at cost? Are you looking at carbon emissions? Are you looking at power use? I mean, we're all looking at power use and PUE. That's a key metric we're all defined. But what about water use and WE? What about space? And I'm open to suggestions. Does anyone else have any other efficiency metrics that might be considered?
Heat recovery efficiency.
Heat recovery efficiency, yeah, that could be one.
Definitely something to do with data, I suspect.
Data efficiency. Okay, that's fine.
Cost is probably one of the big ones.
Cost is probably the big one, yeah. So, well, let's look at cost first, because I think that's another. So just this is an ASHRAE UK, so we're gonna do some maths. So looking at taking the N20 data for London Heathrow, plotting that on a psychometric chart. So to 38 degrees C dry bulb, 23 degrees C wet bulb. To provide cooling, we add water up to the saturation point. I'm just doing this for simplicity, adiabatically. There are other ways of doing it, but let's just concentrate on adiabatically for the moment, which equates to a 0.6 grams of moisture of water added per kilogram of dry air. Fairly simple for psychometric calculation. However, when we do that, that actually provides 14 degrees C of cooling. So looking at where those 2 points are on the chart, and that's purely on the evaporation of water in that particular temperature range. You can also calculate this little plug-in for an ASHRAE there using the formula in ASHRAE fundamentals. They've assumed a few of the numbers. You can calculate it more accurately if you look in the fundamentals book. It goes through how that formula is made up, and you can put in your own values. But fundamentally, it can be calculated. So where does that take us? So if we need 14, let's say we need just 14. Keep it nice and simple. We want 14 degrees C of cooling. We can either use it with water, or as an equivalent, mechanical cooling. So with water, and let's say we want 1 megawatt of cooling, just to keep numbers nice and simple. The airflow is the same in terms of if you're delivering airflow through your heat rejection plant, you're still rejecting that same amount of heat. So you need 0.41 kilograms a second of water to reject that heat. So that's the airflow times by that moisture content per kilogram of air that we looked at earlier. On the other hand, if you're trying to do that with mechanical cooling, let's assume a chiller EER of 4, you need 250 kilowatts of power. So if we base that over an hour, the water use is therefore 1.5 meters cubed of water, or 250 kilowatts of energy, kilowatt hours, sorry, of energy. Which means taking a water cost and an energy cost based on, let's say, London market rates, that ends up to being £3.66 of water, or £64 of electricity. So from an operating cost perspective, water is obviously a much more efficient use of water, to a much more efficient cooling system. Now, if we also consider the carbon emissions, if we take that water as potable water, in terms of, you'll correct me if I'm wrong, scope 1 emissions. Yes, is it? I can't remember.
It is depending on if you're the supplier or not the supplier.
Okay, fair enough. So then the carbon emissions for potable water based on that amount of water is 0.28 kilograms of carbon, whereas the electricity cost based on the grid would be 44 kilograms of CO2 for that 1 hour. And again, looking at the partial PUE and the WE, the figures there based on those numbers. So water is effectively a cheaper and potentially more carbon efficient source of cooling. However, if data centers are only using or purchasing green energy, do those carbon emissions, are they still valid? I know it's part of the discussion, and I'm sure Ian will ask a very complicated question later, or be able to explain it a bit better than I do.
I'm hoping for someone else to ask the question so I can answer it.
Okay. But fundamentally, that's it. As a very simple perspective, that's sort of where we end up. So, therefore, looking at it slightly differently, if we look at now the peak power, we can look at how much power is actually used for that cooling, both from a water and a cooling perspective. So if we again take our evaporative system, we're cooling 1 megawatt of IT, we've got fan power losses, UPS losses, electrical loads and losses. We take them the same on both systems, and we have a cooling power because you still need some cooling even with the evaporative system. And you end up with a peak PUE of about 1.35 for the evaporative system, or 1.5 for the dry system. Again, these numbers are just simple assumptions to demonstrate the principles. I'm sure we could all discuss these for hours, saying which ways, whether they're correct or not. But for principle, this is what I'm saying. So that means you could either then save 10% by evaporating water. You could either save 10% on your incoming power, or if you're a data center owner operator, you could actually generate 11% more revenue, because that extra power that you provide for, you could actually sell as IT power. However, if you are saving power, it's not just the power that's saved. You're going to have a saving on your backup generators, your electrical distribution, and the other equipment needed to to support that cooling load, which actually means you need less space. So you build a smaller building and you save overall embodied carbon. So again, it's carbon emissions or embodied carbon, there's a saving one way or the other. Alternatively, instead, you have the increased revenue because of the additional IT power. So then, in terms of then the water use, is it more efficient to evaporate the water at the data center? So actually, there's an ASHRAE journal published in November 2022 that looked at the water consumption for a 1,500 kilowatt data center in 3 US locations, in Denver, Phoenix, and LA. And actually, as we expected, and sort of as we've shown before, there is an energy reduction over the year of approximately 65% of energy reduction by evaporating water. However, the study also looked at the water consumption, but the total water consumption. So it's not just the water consumed at the data center, that's also the water associated with the power generated required to run the data center, was known as WE class 3. It's not a metric that's used very much, but it's an unrealized fact that by using fossil fuels, the data centers, the power stations that are producing that power using fossil fuels or nuclear are actually consuming water themselves to produce that power. So in terms of if you're starting to look at a water stress region, if you're looking at the power that's produced in that region to supply either the data center or the everything else, that water is still consumed in that region. So we'll come on to water stress in a bit of detail. But fundamentally, for Denver, Phoenix, and Los Angeles, again, they have slightly different power mixes depending on the region they're in. And there is a reduction in the amount of water that they use as a total WE in each of the 3 locations in that study. Now, primarily, I think that's because the US has a much higher fossil fuel energy mix than we do either in Europe or in other places in the world. But it'd be interesting to see, and as I said, there's potential further investigation to determine whether the energy mix in Europe or different locations in Europe with a higher renewables content, which then don't consume water, has a similar benefit. So, final thing to look at is then space efficiency. So, space, the final efficiency metric. Yeah, okay. It's a bit of Star Trek in there. So this was a graph that was actually presented last week at DC London, and it's one that BFC from Baltimore Air Coil produced cooling towers that have shown me before. But it's a really useful way of showing not only how much, if you use more water, you obviously consume less power. Again, the point we sort of just demonstrated, but also the space requirement goes down. So actually, if you have a constrained site physically for let's say a colo located in a city location, you don't necessarily have enough space to put the data center that you may want to go. So you have to go up, and if you go up, you're then constraining your roof size, which then limits the amount of cooling you can put on that roof. So as a quick comparison, just use the visual rule of thumb guide here. For 1 megawatt of cooling, an air-cooled chiller needs 82 meters squared of plant space, whereas a cooling tower is 44 or 48, depending on the type of cooling tower. So therefore, for a given physical roof space, you could get, in theory, twice the amount of cooling on for that same space. So again, it's another efficiency metric that at least we look at in Global Switch to say, well, hold on, I've got physically constrained building, how much cooling can I actually get out of that roof? So those are sort of the benefits. Well, let's see. And this is a sort of open question. Do we count water as a renewable energy source? It's difficult. We all know the water cycle exists. We've all done GCSE science to some level, or whatever it's called. And it's interesting to think that, well, actually, water is a potentially renewable cooling source because it's constantly refreshing. It is, to some degree, an unlimited supply of water on the planet. You know, most of the planet is made up, and there's a slide coming up, I'll show them. But it's an interesting concept to think about. So if we take that water cycle, I'm not going to run through it, I'm assuming everyone's familiar with it. But then if we then build our data center, we're generally taking mains water, and obviously the heat rejection goes out to evaporation. So we're not consuming the water in some regard, but it's still consuming it from another source. So you've got one option, which is taking mains water. Obviously, we are consuming water that's potentially used for residents or other industries or other purposes. So, and that's where a lot of the negative press has come around from. But there are all the alternative sources, one of them being rainwater, another one being river water or other surface bodies. We also have groundwater abstraction. It's not commonly used, but boreholes, it's an option to extract a certain amount of water out of the ground and groundwater, and also treated effluent. This is something that I've been looking at quite closely, is looking at, well, once that water's been cleaned and recycled, can we actually use it for cooling? And I've summarized some of the pros and cons here of the different water supplies. So mains water supply, it's reliable, it's consistent, it's very easy, and that's why people tend to use it. However, it's a high cost, and generally the focus for most potable water supplies is to supply people, not to supply industry, which includes data centers. So the other options, groundwater extraction, again, that's possible, and it's only suitable if water is available in sufficient quantity. You may need a permit, and abstracting this may actually reduce the water table. This is part of the issue that they're having water stress in the States at the moment, is they're extracting so much water from the Colorado River Basin, it isn't getting replenished quick enough. So you see lots of images of the Hoover Dam getting lower and lower and lower in the amount of water it's holding. Surface water extraction, again, this is what actual power stations generally tend to use, either rivers, canals, or even seawater. It's a lower cost, and it's potentially better because it's not using mains water. There'll be a lower carbon emission from it because you're just taking raw water out, using it and returning it back. But there's permits, and it may require some treatment. You know, if you're taking water out of the Thames in London, you probably don't want to do that. It's very messy. On the other hand, rainwater harvesting, this is sustainable. You know, I'm sure those of us that have gardens have a water butt to collect water and use that for watering the garden. Same principle applies, it's just on a bigger scale, but it's dependent on rainfall patterns. And generally when we want to use the most water for cooling is in the summer, when we don't necessarily have as much rain to make it worthwhile. The other one is treated effluent, and this is one where I think there is a real benefit to data centers, and it's something that I know Anglia Water put in an article recently, saying that that's the water we should be using. It's already been cleaned to a degree. It's not drinkable, but it's clean enough that we could use it for cooling. And it promotes circular use because, again, we're giving them our waste product in terms of wastewater, toilets, things like that. But in return, we're taking their waste product, which is water, and using it to cool our equipment. So there are a number of other options that can be used. So where is Earth's water? This is, and I'll make no shame to say this is taken straight from Wikipedia, but it really shows exactly how much water actually is available. So you start down the list, obviously Pacific Ocean, largest body of water. You work your way down. Groundwater is actually fairly high up there. 1.7% of water is available in the ground. Okay, most of that is saline in marshes and things like that, but there's a high percentage of that is fresh groundwater. But then you go follow down the list, you've got lakes, and then down to atmosphere. So all that moisture in the air, clouds, it's only 9 parts per million. And down to rivers, that's even less, that's down to 2. So again, there's an argument of should we be taking water from rivers? We'll see. So water stress. So where does it go? So this is taken from the World Resources Institute aqueduct program. So this shows water stress for the entire planet based on the available data. Water stress, as a definition, is the ratio of total water demand to the available renewable surface and groundwater supply. So again, where this calculates in terms of water stress, it's not just looking at how much water is coming out the river, or how much rainfall is produced, or how much groundwater is available. It's actually looking at a combination of those and how well they're maintained. And so generally, what you can see is the water stress areas are generally high population areas where more water is being taken out than is being replaced. Obviously, warmer and Mediterranean climates are going to struggle with water more because they have received less rainfall, so there's less opportunity for that renewable supply to be topped up. But in northern regions and for most of Europe, there is very little or a low level of water stress. So what targets should we look at? Obviously, the CNDCP is the Climate Neutral Data Center Pact, has set targets for WE, which a lot of operators have signed up to and will be used. These are also being recommended as the EU limits under the labelling scheme for the EED. And the limit is set at 0.4 litres per kilowatt hour as the limit for colder climates using potable waters in area with high stress. There are other correction factors if you start looking into it. So if you're in a warmer climate, you can use a little bit more water. If you're using another source other than potable water, you can actually use a lot more water because you're not taking away from potable water. And again, in water stressed areas, in less water stressed areas, you can use more water as well. So there are targets that the industry is starting to follow, but it's the question of, it still remains a divisive question of, well, should data centers use water? The simple answer is yes. For occupants, maintenance, and circulating and cooling systems, so water use, yes. But should data centers consume water for cooling? Oh, that's a much more difficult question. You know, there's a whole range of factors that need to be considered. I'm not going to give you the answer here. There isn't one right answer. As I say, with most engineering problems, there is always a compromise across the various factors to be taken into account. And fundamentally, that is where I am going to end, because it is not something that is ever going to be decided based on that. There is not one rule that fits everything. It is always going to be a compromise based on the location and a number of factors. And it's going to be interesting to see how the markets react, how data center design develops in the future.
Stephen, thank you very much. I'm going to jump in and take some liberties to point out a couple of things from my position as in sustainability and in engineering, so I can do them both. Can we pop back very quickly to the psychrometric chart? Mm-hmm. There's one point on here which is very, very important to this conversation, and it's the length of time we're thinking about this. We're in climate change, as we all know. The world is changing. For every 1 degree increase, the amount of water that air can hold increases much more than 1%. I don't quite know what the ratio is. The ratio changes depending on the temperature. But essentially speaking, we're going to live in a world where if we were 20 degrees average one day and we're 21 the next, we have significantly more rainfall or mist or just humidity in the air. Has two effects. The first one is it's more difficult to cool by water, but you've got more of it. That's the first one to consider. The second one is, and I'm going to reiterate a point you've already made, but just in case anyone meets it, I'm going to paraphrase to kind of put it in different perspective. If you use cooling on a data center, water-cooled solution, so you've got your evaporative cooling systems, but your fossil fuel power stations use no water at all, that's probably okay. However, if your fossil fuel power station uses water, or in fact, if your renewable energy comes from something that uses water, there is a chance that you'll be better off using dry coolers in totality, and the inverse depending on where you are. So there's a very real possibility in the UK with the increase in temperature, and if we continue to use any fossil fuels, that there will be a sweet spot where water cooling is correct and dry cooling is correct, and every single project needs to check. I'm just giving you context. I'm not asking a question. I think there's going to be plenty of those for you anyway, and there's one over there for you already, Steve. Actually,
yeah, but coming back on your point, I think one of the most interesting things is that in terms of climate change, and as engineers, we design obviously to that N20 condition, and that is obviously the worst expected temperature in a 20-year period. But what with climate change, with the predictions that are coming out of all the modelling that's being undertaken, is that actually the dry bulb temperature experiences a much more variation to the tune of 3 or 4 degrees, whereas the wet bulb is only 0.5 or 1 degree change in extreme temperature scenarios. So again, it's probably another slide I should have added. It's probably water-cooled equipment can potentially protect you better against unforeseen climate change extremes.
Definitely. We have a question in the room, and then I'll come to the questions.
Thank you, Steve. And just the point regarding the so-called embedded water in the grid. Is there available data to be able to actually quantify and qualify and do that assessment? You mentioned the 3 examples in Colorado and so on, but in the UK or Europe or APAC, is that data readily available so we can assess how water intensive the grid is?
I would like to say so. I'll admit I've not looked into it to see if it is available. At least in the US, it's very well documented. They manage that quite carefully, but that's mainly because they control all the water basins and they have very strict federal laws about passing water from state to state to state. There's different requirements, so they monitor that quite closely. In the UK, I don't know. I'd have to look into it, but I'd like to think that someone in the UK knows how much water we're using.
That's why we're not using WUV3 as a methodology, because we haven't got data to back it up.
You're probably right, but it's something that we should be pushing for to be able to make these sorts of fairly fundamental decisions on whether to use evaporative cooling or not.
Thank you.
So I've got a question from Tim Mitchell. Tim, would it be easier if you just, if you're happy to just explain the question yourself?
Thanks. Really interesting presentation. Thank you. And I've not got any axe to grind either way, frankly. But the question, there's a few questions in my text there that might suggest otherwise. But I promise you, I'm not a proponent for one or other system. Just interested to hear what you've got to say. So the comparisons of wet versus dry systems are very interesting. But very often we see that systems will need some kit, dry kit, to take care of those times that the wet kit can't do the job. And so I wondered whether the comparisons had taken that into account in cost, space, carbon, all that kind of stuff, whether that was covered. And also, if you have a purely wet system, the standby water storage requirement that's often needed there might also have to be taken into account. And just as another sort of point, the 82 square meters of chiller space for a megawatt of a dry chiller does seem a bit high, but yeah, not a major drama, that one. But yeah, I'd be interested to know whether that dry kit, standby kit, if you like, or the high temperature kit would have been factored in.
So yeah, so looking at some of the sorry, I've got the it's going to make it work. If you go back to the peak PU analysis, yes. So fundamentally, you're right. There is some allowance in. You cannot provide all of the cooling just by evaporating water. There is in the peak PUE. Next one.
Trying to get there. Trying to get there.
There isn't a no. It's next one. Yeah, there is an allowance for putting some mechanical cooling in the evaporative system because it can't all be done with water. So yes, at the peak temperature conditions. I think your second point was on for water storage. Yes, again, for data center engineers, uptime requirements is 12 hours of water storage, and that's to be concurrently maintainable. So yes, so that is a requirement. So yes, that does take up some space. And that is a challenge I have come across on a number of sites, but it generally is less. To build a tank is generally less embodied carbon, potentially putting in additional generators and the electrical switch here.
I also see in quite a number of data centers the requirements for stormwater attenuation, so the two things can be used for the same purpose.
Yes, we are starting to do that. Yeah.
It's a similar question from Jake, also on the energy use in actually processing the water, treating the water, but also the space allowance for that water treatment would be another one to add into that equation.
Yes, that's true. I could add that in. Yeah, generally the process water plant room space, it depends on the level of treatment you want to go for and what your cycles of concentration you're targeting. So for example, if you want to be really efficient with the amount of water you use, and Eugene will know this because we've talked about this a lot on previous projects, the higher you can get those cycles of concentration, obviously the more efficient, the less wasted water you end up with. But you could just use more water and waste more water. But yes, it is more efficient to treat the water and process it than just use raw water.
I got a question about the energy analysis. It might be the slide before this one. If this analysis is based on a comparison where the electricity you're buying to power the data center comes from whatever the grid supplies, be that in the US predominantly perhaps fossil fuel. If you were buying completely renewable energy, certified renewable energy, guarantee of origin, Would that electricity then have
There would still be some.
no water usage associated with it, or would it still have?
There would still be some things like, for example, nuclear still uses water, seawater for cooling. So therefore, it still does use some.
Every energy using solar panels use water.
Yeah,
Because you have to
in the
clean them twice a
manufacture.
year at least. And if they're in a very dusty area, you actually use quite a lot of water to clean them. You can dry clean them as well. Wind turbines is probably the lowest water
Yeah.
use.
And again, is there a good resource that you'd point to for the comparison of the water usage effectiveness of those different energy sources?
There is the data out there, but yes, good resource in this respect.
A trustworthy.
It's as good as it is anywhere else. I'm going to put it like that.
I think it's definitely one where there's an area for further study to determine, what the standards might be and what the numbers might be. Again, the American standard does have some figures, and again, for a coal-fired power plant or a combined cycle gas turbine plant in America, I'm sure it'll be a very similar amount of water use compared to the UK because it's the same plant per megawatt. But yeah, in terms of actually trying to quantify figures, it's not something that I've come across as easy.
Eliana, I have a question from your hand up. You got a question?
Hello, yeah, thank you for your presentation. You've touched on 2 points. Essentially, I wanted to ask about the future of the industry, any trends you foresee. You spoke a bit about liquid cooling. I've seen reports talking about this being the dominant model by 2030, as well as it was really interesting to hear about treated effluent as a water source. So yeah, just interested to hear from the room and from yourselves, any other things you think are interesting or to look out for. I'm particularly coming from a more sustainability perspective rather than MEP, but yeah, it'd be great to hear.
I think one of the biggest trends, and I tried not to touch it on the presentation because otherwise everyone sort of dives down a liquid cooling rabbit hole, is liquid cooling. But from a heat rejection perspective, again, the higher you can get those cooling system temperatures, the less energy and less water should be being used, whether you are using dry cooling or evaporative cooling systems. So therefore, as the industry hopefully moves towards having more liquid cooling within data centers, there should be less water and less water use, but also more efficient PUEs.
Maybe if you want to add to Eliana's question is, what's your insight or crystal ball? Are we going to see higher chilled water temperatures or go back cooler? Because if we go high enough, we can be free cooling 100% of the year.
That's correct. It's something that I've been looking at with Global Switch. It's interesting to see how high that can be pushed, but it is going to always be limited by customer requirements, but also things like what they manufacture of the equipment, what NVIDIA say they want to run their chips at in terms of the temperature. So it will vary. We're still new in it from that regard, but hopefully as time progresses, we'll be able to get more definite temperatures of what we want to operate and push those higher. Again, yeah, reduce energy, use less water. And again, I think you were talking earlier about heat reuse potentially. It's all to be added into the mix. But I say, from a water perspective, at least liquid cooling, high temperatures means less water use.
We're doing a terrible job of giving a clear answer here, and I'm going to make it worse. So there's a push and pull to answer your question. The more the industry looks at ICT as a process and dehumanizes it, makes it ultimately what it's for. It's a machine and it has to do a machine's job. In the same way you would smelt something, it has to get hot and you don't put a human in there. If we treat processing like that and AI, high density, et cetera, and really treat it like a process, you can remove the human, then your temperatures go where you want them to go. And you potentially got a much higher temperature. And yes, we could go all air. That'd be fantastic. However, the same guys that are designing this are realizing them to sell them, they need to put them into existing data centers, which were designed around humans. The standard recommended temperatures, first of all, assume for fire and life safety. They assume for longevity of the material and equipment in there while a human's maintaining it. And that's the current legacy problem that we have of switching from data centers to IT processing centers. I guess is a new phrase I've just come up with. And I'm going to trade. So that doesn't help you, but realistically, if we wanted to get this as efficient as possible, we remove the human problem and change the temperatures. We do have one other question there. I saw from, actually, I was going to get, I'd like to come back to treated sewage effluent with Tim at some point, because I know he has an opinion on this. But first of all, Lee, Mr. Prescott.
Hi guys, thank you. Really good presentation, Stephen. I enjoyed that.
Thank you.
I just want to give my view on things. And I think I'm for the use of water from a consumption point of view, but where it's geographically responsible. Where we have plentiful water and it's not stressed, the physics speaks for itself. It takes 2,230 kilojoules to evaporate 1 litre of water. So for 1 litre of water consumed, we can get rid of 2.2 meg of heat. And it's a really powerful physical metric. And that's why everything that Stephen was talking through is so compelling when you look at plant space and energy efficiency. So from that perspective, I'm for it where it's geographically responsible. And then you sort of touched on the water use versus consumption. Just really on that side of things, why do we use water rather than air to cool our servers and chips and things? Well, again, the properties of water really speak for themselves. It's 4.2 kilojoules per kilogram K thermal transfer properties for water versus 1 for air. Water's density is roughly 1,000 kilograms per meter cubed, it's pretty much bang on, and air is just over 1. So the difference is 4,000 times between trying to cool a server with air through conduction or trying to cool a server with fluid. So everything lends itself to water use or water consumption, but it does come back to it has to be responsible. So where we're not water stressed, I think we should be using it.
Thank you, Lee. It's a good summary.
Last question.
I was going to say there's a question on there about noise.
I'll tell you what we need is someone who sells chillers, or someone that might be industry that.
How about a qualified acoustician?
Yeah, there we go. There
Yes, noise is an interesting one. Fundamentally, most of the noise from a heat rejection plant is just through the movement of air. However, with dry cooling, with chillers, you do have the extra compressor noise, but generally they sort of balance out. The chiller manufacturers work for carrier, you said, generally try and balance the noise of the compressors with fans so that it's pretty much the same noise level. I mean, again, generally when we're putting so much heat rejection on a roof, the aim is trying to get rid of that heat as efficiently as possible. Noise is one of the lesser concerns, but adding water to cooling towers can sometimes generate additional noise. So again, it will be subject to those local requirements.
I think it's a fundamental point, but when you're designing these data centers, it isn't such an issue. You can get it through planning with the right design and the right kit from the right manufacturer and the right considerations, how you design it. The biggest problem comes with maintenance. A lack of maintenance on water-cooled systems tends to be a result in more noise, in my experience. So yeah, it's in planning, it's not in design, it's not so much of an issue. In operation, it can be more.
Yeah, and actually touches on one of the points that Lee, I think you raised as a potential efficiency metric is sort of Legionella and water treatment. Yeah. Legionella, the risks of Legionella and having someone come in and shut your plant down because you're not maintaining it properly does actually become a risk for data center operators in the event of a Legionella outbreak. So it's just another one to consider.
I think on that one, Stephen, it is potentially a risk, but I think with the maturity of the data center market and the fact it's mission critical, how much effort goes into maintaining sites, I personally think it's a risk that's eliminated. In other industries, it's probably a risk in reality, but in the data center industry, if you don't maintain your plant and look after your systems, your site will fail. Whether it's because you're being shut down or over Legionella or something else, your site will fail. So I actually think that's a very controllable risk for this market.
It is.
Yes, agreed.
The last question on there is, are we likely to see water cooling become feasible in the future? It's been feasible forever.
It's been feasible forever, but you've got to build a data center on the coast.
It's an excellent way of cooling. I've done one. I've done more than one. it presents a whole different set of risks, and largely around what temperatures you're doing, the volume of water you're dealing with. You have exactly the same, but even worse risks in rivers about temperature and what it's going to do to local ecology. However, if you can do it, it's absolutely recommended, and I prefer, if you can, to have deep sea water extraction, which is incredibly efficient if you can get it working early. And you do need quite deep water to get that working.
It's also much cooler.
Deep water cooling tends to have a stable
temperature.
Yeah, all year round, and it really is superb.
Yeah.
Thank you very much.
Building on that, what are the arguments for and against desalination then, if you've got a potential site for seawater support?
So desalination is, and I'll draw on a bit of experience here. So in Global Switch, our data center in Singapore, we actually take desalinated water, and because obviously Singapore is an island, high population, low amount of potable water, they have huge desalination plants, and it's a multi-stage plant. And what they actually do is after the first couple of stages, where all that reject water actually goes out as they define it as new water, which is basically water that they set aside rather than just discharging it back to the sea. It's clean and you can use it for application, so they provide it to industry. So it's cheaper and more sustainable, and it's not potable water. So actually we use that in our data center in Singapore. So we're already using. So desalination, yes, if you can support the local water and be sort of a little bit more water positive, it's another one I haven't touched on, because I think that's a bit of a minefield if you start declaring yourself water positive. There isn't really, it's not even go there. But you can actually then, again, it can highlight things like ESG. You can provide that water to local suppliers, businesses, and homes. So, yeah.
I mean, all the water that's supplying data centers in the Middle East is desalinated.
Yeah, of course.
From waste heat rejection from power plant.
It's funny, we've got one in Singapore where we're exploring similar things. Yeah, it's food for thought.
One more time for one last question, do you think?
Yeah, what time have we got?
Yeah, let's go for one last one. It's from Tim. Tim, tell us what you think. You're on mute.
Tim's on mute. Yeah.
My thoughts are the same as well, as far as using water for evaporative and the benefits that you see with the PUE. There's obviously things that dictate whether it is possible or not to use, and what sweet spot will be. There's a sliding scale on how much water is required for different types of water consumers in the heat rejection process to factor in, that mean to say that it will be possible not to deploy by location. It may be that the site, you don't have the space to accommodate the water storage. If you're reliant on that, you're sizing equipment for running evaporative only rather than selecting for sensible as a backup. But yeah, it's misconceived quite widely, I think, actually, DCs and what they consume in water. But yeah, it has its place, definitely, in decarbonising the industry.
Yep, agreed. And I think that's part of the message, that at least having this topic of conversation has helped to highlight is that, we all see the benefits of it, but where it's being crucified in the press for data centers using water and people are getting hosepipe bans, well, that's fundamentally where the management of the water system needs to be a bit better. If there were more, I think we said, treated effluent systems and other sources of water that were more readily available, we would be using them instead of potable water. But they're not. It's almost a similar argument to the heat network. We would all be connecting to a heat network if there was one straight outside. But as they're not as well developed, at least in the UK, as they are in other European regions. It's harder to do it, and so it gets put into too hard category.
Yeah, we've got a number of projects that we've delivered over several years, which are using alternate water sources. Most people just think of like utility water, but there are lots of other options dependent on the location, water stress and availability. But some of the ones which may not be necessarily thought of, we've got examples in the Nordic countries where we're using ice snow rainfall harvesting. Which without any actual utility backup. And we've also, I think it's raised in the chat by someone about use of sea ocean water as well. We've got a number of instances where we've done that, and also groundwater in the Netherlands and other places.
Yeah, the groundwater in the Netherlands is kind of essential for the Netherlands to be the Netherlands.
Yes.
So I support that one, but listen, I'm going to first of all pause to thank Stephen for his presentation. We'll put a round of applause there. Thank you all to those online and came in person. It's great to see you all. You will probably see more on this topic soon. From my perspective, I'm not going to go into the technical because that wasn't necessarily the entire purpose of this. I think what we've convinced ourselves is this is an engineering problem. How we then actually persuade the public to understand this is going to be a real challenge. We can sit here and ask questions and not come to an ultimate conclusion. We've got to find a way of getting that out into the public domain where people can read a report and actually understand the implications of it for their own community and their own interests. That is a real challenge for the sector. We know the engineering problems don't have a black and white answer, let's say. We've got to go red. Anyway, right. Thank you all very much, and hopefully I'll see you soon. Take care, guys.
Cheers. Thank you.
Thank you. Bye-bye.
Thank you. Bye.